Hi there, we're going to take a few minutes to discuss some topics in this chapter, which are scatter plots and correlation. Now you can see underneath here I have a series of different scatter plots that we're going to talk about, or examples of scatter plots, and then we're going to talk about this concept of correlation, which is a neat little calculation we can do that can quantify the relationship in these graphs, the relationship between our two variables. Now I mentioned two variables. We call this bivariate data. And bivariate data, again, as I mentioned, involves two variables whose values can change. The purpose of bivariate data is to explain the relationship between these two variables. That's why we collect it in that way. And our variables in this chapter are both quantitative. So if we think about that, it brings us back a little bit to algebra. You think about that good old-fashioned ordered pair x comma y. That's what we're going to be working with. Of course, we will call them in statistics our explanatory variable and our response variable. So it's sort of another ordered pair, just with a little bit more explanation in here as to what each of these are. So on the x-axis we'll have the explanatory variable, on the y-axis we'll have the response variable. And these are terms we've used throughout the duration of the course already. And the first graph I'm going to show you, we're going to look at unemployment and violent crime rate. So our explanatory variable will be unemployment, and our response variable will be a violent crime rate. Let me show you this scatter plot. Here it is. As I mentioned, our explanatory variable there on the x-axis, the employment rate, and our response variable. So what this graph is a representation in 2014 of all 50 states in the U.S. So there are 50 dots here, possibly 51. I don't remember if District of Columbia is in there, but there are approximately 50 dots here. Each dot represents a state. I've labeled a few of them. This one up in the right-hand corner, that's Nevada, and you can see it has, we can trace down to the x-axis and see that its employment rate in that year was quite high at 8%, and the violent crime rate was at 600. Now what 600 means is that there were 600 violent crimes per 100,000 people. So that's our crime rate here. And then this dot right here, as I mentioned, I just picked out another random dot. This is Kansas, and you can trace down and across and see those two quantitative measures, sort of guesstimate what they are by where they fall on the axes, and you know a little bit more. Now the purpose of these, again, we want to describe the relationship between our explanatory variable and our response variable. And oftentimes one of the simple relationships we like to use, if it's merited, if it's one that our data might mimic, is that of a line. So here what I did here was put in and add into this what we call the line of best fit. You might have heard your algebra teacher call it that before. We'll call it something slightly different in a future video, but for now we'll call it the line of best fit. So you can see that there is a slight trend as the unemployment rate is increasing in these states, different states. The violent crime rate has a slight increase as well. Although it's not a perfectly linear relationship, we do see that slight trend is evident. So I want to take us to a much smaller data set that only has 15 values, and you might remember seeing this in a previous classroom group work. I'm going to revisit it again. This data set compares the high temperature of the day to the amount of hot coffee sales that a local coffee shop was able to pull in. So we're going to take a brief pause here, and we're going to get to StatCrunch and pull up this data, and I can show you how you can do a lot of neat things with it. So here we are in StatCrunch. Let's go back here. So you're going to sign in. I am already signed in. Sign yourself in. You're going to click on Explore and then Data. And then you're going to type in the name of this data set called Coffee Sales. Click on it, and that data you saw on the slide is right here. So what I want to do with this is I want to do two things. I first want to create a scatter plot. So we want to create a graph of this data. So we're going to click on Graph, scatter plot, which is almost halfway down in this menu box. And the only thing left to do is to tell StatCrunch what should be on your x-axis. In other words, what is your explanatory variable and what is your y-axis, your response variable. So we talked about this in the prior lecture, that we believe that our x variable is temperature, and that the coffee sales were probably best described and explained by coffee sales being the response variable. They're probably best explained by the high temp. The opposite relationship doesn't quite make much sense. The high temperature of the day cannot be explained or is not determined by how much coffee is sold. So you just pick the right roles of the variables here and press compute. And here's a visual display of that data set. There are 15 dots because there are 15 values here, so 15 different days. You can sort of see there is, as the temperature is increasing and it's getting warmer and warmer, that is the high temp of the day, their coffee sales did decline a bit. And this is hot coffee sales. So it's a quick, neat way to get the data graphed very quickly. The next thing I want to show you is something called correlation. Now, I'll define this in a future slide, but I do want to show you, while I have this data up, how we can compute that very quickly. So you'll click on Stat, Summary Stat, Correlation. You need two variables, this bivariate data. In this case, two quantitative variables. Just click and drag and choose them. So we're in this module called correlation, and choose the variables you want to correlate and hit compute. So it tells us here in this pop-up box, a nice little sentence using our variable names, that the correlation between high temperature of the day and hot coffee sales is negative 0.937. So remember that. We'll come back to that in just a minute when we further define correlation, but it's a very quick calculation that can be done in StatCrunch. Also, while we're at it, we go back here to our search box. We're going to look for our data that we had in our first scatter plot, that is unemployment, and I think if you just put in unemployment and my name, M. Gore, I think that's enough. That is enough of unique terms to get to this data. Oh, it is. There it is. So unemployment and M. Gore. So these were the 50 states I was talking about earlier. And I have several variables here that I was looking at, but the first two are after the state name are the ones that I was taking a look at. So if I want to get a correlation for that, we already know what the graph looks like. Stat, summary stat, correlation. I'm going to grab the two. It doesn't matter who's x and y in this calculation. They just want to know the two quantitative variables. And hit compute. We see a correlation here, much different. Well, this one's positive, 0.455. So let's go back to so what correlation is? Let me define it for you. You saw it there computed very quickly. It measures the strength of the linear relationship between two quantitative variables. That's how we define it in a statistics class. So it has this, it's saying how linear-like are the dots on your scatter plot. Are they really spread out and not looking much like a line, or are they sort of following the trajectory of what would be a line? So remember, we had coffee sales and high temp. There was a correlation that StatCrunch gave us. And R is for correlation. And then unemployment rate. So again, very different. If you remember those graphs, they looked very different. So their correlations are also explaining something. You know, one's negative, one's positive. We'll come to this in just a minute. One's at 0.9, one's at 0.45. And let's take a moment to talk about this measure correlation. Correlation by sort of mathematical design is a number between -1 and 1. So the forefathers of statistics engineered this neat measure that can tell us the strength of the linear relationship, and it kept itself, it bounded itself between -1 and 1. So let's talk about what can happen in that small interval from -1 to 1. So let's start over here on the right. If we were to have a correlation of 1, that is r equals to 1, then our dots in our scatter plot would line up in a perfect line. In other words, I could put a line through these dots here, these 10 or 12 dots, and it would touch each and every one of them. That is considered perfect positive correlation. Rarely ever achieved, but that is the end of our spectrum. That's what a correlation of 1 looks like. I bet you can guess what a correlation of -1 might look like. Same idea here. The dots do line up themselves as a line, but it has a different slope. In other words, this slope, we would all agree from algebra class, is negative. So as one variable is increasing, the other variable is decreasing. Right here, for perfect positive correlation, as one variable increases, the other variable increases. So those are the ends of this spectrum. Let's look in the middle. In the middle, that's zero correlation. So you can see this is just a bunch of chaotic dots. I'd like to say there's not much trend or relationship between the two of them. And that's essentially what a correlation of 0 looks like. Now, as we travel from the middle here, 0, out to what we see as either negative perfect correlation or positive perfect correlation, the dots you will see start to go from no relationship and then start to faintly resemble sort of a positive linear trend. Now these dots are very kind of cloud-like and spread out, but as you can see, there is a general trend here from the lower left to the upper right. And as we move further out, the dots are starting to get closer and closer to an imagined line there. So that's what it means when you go from the middle of this interval out to the edge. The dots just appear to be a little more, for lack of a better word, organized, or a little more starting to follow a more obvious linear trend. So this is moderate positive correlation here as you move out and you get to the edge. And this is moderate negative correlation. Again, the negative being that it goes from upper left down to lower right. One last aspect is we can talk about their direction, that is negative and positive, but we can also know that in the middle, that correlation here around 0 is considered very weak. And as these dots and as the correlation moves out to 1, that correlation, we say, becomes stronger. Likewise, it becomes stronger as you move to the left. So as you go out to the ends here of this little interval, your correlation is getting stronger. So this might make sense now that we go back and look at this, that the coffee cells in high temperature had a negative correlation. Remember, as the temperatures increased, the coffee cells decreased. And that particular set of dots seemed to resemble a line very nicely. And the unemployment rate in violent crime, as the unemployment rate was increasing, the violent crime, we could see a slight trend there increasing as well. Now, those dots were not nearly as clustered around a perceived line, so their correlation is positive, but yet kind of a moderately weak correlation. Some more properties about correlation, just some quick facts. The sign of the correlation, again, gives the direction of the association. In other words, the direction of the line. Is it increasing, or does that line decrease? Correlation treats x and y symmetrically. In other words, it doesn't care when it computes this correlation for us which variable is chosen as x or y. That correlation would be the same whether you reverse the order of the two variables. And correlation has no units. It simply just measures the strength of the linear relationship. And correlation is very sensitive to outliers. I do want to give a slight nod here because we do focus a lot about a linear relationship, but a lot of variables can have very significant and strong relationships with one another and not necessarily have a linear relationship. So I just want to point that out. We can have variables that seem to have more of what might look like a quadratic relationship here, and variables that might have an exponential relationship. They're very interesting, but our value r does not describe these relationships. It's only going to describe if it's linear. The last thing I want to talk about is this idea that correlation does not imply causation. So in statistics, it's kind of unfortunate that we call the y variable the response variable, because it sort of, in that name, makes us feel as though the variable is in fact responding to x. And sometimes we use that language to determine which one's which one's explanatory, which one's response. But because often these situations involve observational data, we aren't able to tease out whether or not x causes y, or the explanatory is causing the response to change. Here's a few examples of what I mean. So, situation 1, ice cream consumption and murder rates are highly correlated. We've seen this in lots of situations. People have actually looked at this data and they find that. So, we would say, now, does ice cream incite murder, or does murder incite the demand for ice cream? If we thought causation was in the situation, we would say one of these two statements. Neither one of them makes sense. So what that shows us is that there could be some other variables causing both of these phenomena, that is, ice cream consumption and murder rates, to change, but not that the murder rates are changing your ice cream consumption, nor is the ice cream consumption really affecting the murder rates. Could you think of such a variable that would cause both these two to change? Well, if you were thinking the temperature outside, you'd be correct. Just so happens that in warm temperatures, as we all know, ice cream consumption does go up, and it's been proven that murder rates go up in warmer temperatures. So we have a variable, a third variable here, that's affecting these two, and not as though ice cream is causing murder rates to increase, nor are murder rates causing ice cream consumption to increase. This variable is called a lurking variable. It's a third variable that's causing both of the individual ones we're looking at to change. Here's a second situation. Nations with more televisions per person have greater life expectancies. So this is a correlation that someone has found that seems to be significant. In other words, the R is relatively strong. Now you would ask yourself, would shipping more televisions to a country with low life expectancy cause people to live longer? And we all kind of feel that no, that wouldn't cause people to live longer. So what is a third variable, or maybe even more, but certainly another variable that could be causing both of these two variables, that is, the number of televisions per person and life expectancies? What could be causing both of those to change? If you were thinking the wealth of the nation, you'd be correct. Countries with higher wealth possibly may have more televisions per person and also have greater life expectancies, and people may have more access to health care and so forth. So the wealth of the nation, or the wealth, is a possible lurking variable here.